Hello there, Mr. Sutton here, bringing you the IM3 8.5 Extra Practice number 1 solutions on probability of disjoint and overlapping events. For this situation, we want to find the probability where a box of chocolates has 7 milk chocolates, 6 dark chocolates, and let's see here, we're told 1 of the milk chocolates and 2 of the dark chocolates have peanuts inside. Uh-oh, look out for allergies. You randomly select and eat a chocolate. We want the probability now that it's a milk chocolate or has no peanuts inside. So since we're dealing with an or, we have to ask, is this disjoint or is there overlap between these two categories? Can we have milk chocolates that have no peanuts? And the answer is yes, something could be both of these. So since they're overlapping, we're going to have to subtract whatever the overlap is between these two groups after we add them together. So let's do this now. Probability of milk chocolate or no peanuts. Let's do the milk chocolate probability first. I think that's the easier of the two. So overall, total possibilities, we had 7 milk chocolates and 6 dark chocolates. That's a total of 13 chocolates altogether. And out of those, for milk chocolates, there's only 7 of those. So 7 out of 13 chance of getting a milk chocolate, whether it has nuts or not. Now let's talk about the peanuts. The probability that something has no peanuts. So we again have 13 total possibilities, but now let's look at the breakdown here between the two different groups. So they said 1 of the milk chocolates has peanuts. That means that 6 of the milk chocolates don't. And they said 2 of the dark chocolates have peanuts. That means that 4 of the dark chocolates don't. So 6 of the milk chocolates, 4 of the dark chocolates, that's a total of 10 chocolates that do not have peanuts inside. So we're going to add 10 over 13. Now we have to subtract the overlap because we've got the milk chocolates, we've got the no peanut chocolates, but some of them fall into both categories. So how many milk chocolates have no peanuts? Well, we said this a moment ago. If, let's see, 1 of the milk chocolates has peanuts, that means that 6 of the 7 don't. So that's 6 over 13 that we have to subtract from what we already added together. And now if we add these up, we've got 7 plus 10 is 17. Minus 6 is 11, so that's 11 out of 13 chance of getting milk, chocolate, or no peanuts. On this problem, we have 12 shirts in the closet, 5 that are blue, 3 green, and 4 red. We randomly select one. We want the probability that it's blue or green. Well, we don't have any shirts that are both colors, so these are disjoint or mutually exclusive events, which means we just have to find the probability of either one of these happening and then add those probabilities together. So we're doing blue or green. Probability of blue. Well, we had a total number of possibilities of 12. There's 12 shirts in your closet. And out of those, they said that we had 5 blues. So you have a 5 out of 12 chance of getting a blue shirt. Now for green shirts, we had 3 greens. So that's a 3 out of 12 chance of getting a green. And we can add that to the 5 out of 12. Overall, then, that adds up to 8 over 12, which we can now reduce to 2/3. For this problem, we have a magazine with 15 pages, and we randomly open to a page. The page number, we want to find the probability that the page number is 1 or 8. So if we're dealing with an or, we have to ask, are these disjoint categories, or can there be some overlap? Can a page be page number 1 and page number 8 at the same time? Well, definitely not. These are very disjoint. So we just have to add the individual probabilities together and call it a day. So let's do then probability of 1 or 8. Our total number of possibilities, since there's 15 pages, we're going to have a fraction over 15. And the probability of getting page number 1, well, there's only one page that has the number 1 on these pages here, so that's a 1 in 15 chance. There's also only one page 8. So we're going to add to this another 1 over 15 chance. And then those just add up to 2 over 15, and we're done. For this problem, we have a spinner with an equal chance of landing in 5 different numbered regions. And after spinning, we want the probability that it lands either in region 3 or 4. If we're dealing with an or, we have to ask, is there any overlap between these two groups? And there is not. Regions 3 and 4 are completely separate. It's one or the other, or some other region. So since these are disjoint, we just add the individual probabilities without having to subtract any kind of overlap. So probability of region 3 or 4, let's do probability of region 3 first. Now, the total number of possibilities is going to be 5 because there's 5 numbered regions, so that's our denominator. And the probability of getting region 3 by itself, since it's just one of the 5, that's 1 over 5. Probability of getting 4 is also 1 over 5, which we can add to the first 1/5, and then those just add up to 2/5. On this problem, we have 6 nickels and 6 dimes in our pocket, and one of the nickels, 3 of the dimes are Canadian. We're going to have to keep going back to this sentence, by the way. And then the others are U.S. currency. You randomly select a coin from your pocket. We want the probability that it's a dime or Canadian currency. So we have to ask ourselves, since we're dealing with an or statement, is there any overlap between these two groups? Because we can figure out the probability that it's a dime or the probability that it's Canadian currency, but do we need to know the probability that it's both? And we do. There are definitely some Canadian dimes that they mentioned up here. They said one of the nickels and 3 of the dimes are Canadian, so there's overlap that we will have to subtract later on. So since there's overlap, let's worry about that when we get there, but we're going to be subtracting. Let's find now the probability of a dime or Canadian currency. Let's find the probability of just getting a dime by itself. They said we had 6 nickels and 6 dimes. So our total possibilities, there's 12 coins that we could get. And out of those, 6 are dimes. So we have a 6 out of 12 chance of getting a dime regardless of what country it comes from. Now for the Canadian currency, there's still 12 coins overall. They said 1 of the nickels and 3 of the dimes are Canadian. So 1 plus 3, that's 4 Canadian coins that we have. So we're going to add 4 over 12 for the Canadian currency. So now we've got the probability of dimes and Canadian coins, but some of the dimes are Canadian coins. So we have to subtract those so we're not counting them twice. Now they said here that 3 of the dimes are Canadians. So we're going to have to subtract 3 over 12. And now if we put this all together, 6 plus 4 is 10, minus 3 is 7, so that's 7/12 chance of getting a dime or a Canadian coin. For this problem, we have a litter of kittens, consisting of 1 gray female, 3 gray males, 3 black females, and 1 black male, so they really spelled a lot out in that first sentence. And then we randomly pick one. We want to know the probability that it is a black kitten or a male kitten. All right, so is there any overlap between these groups? We're dealing with an or statement, so we need to know if these are mutually exclusive or overlapping. Can we have cats that are both black and male? And the answer is yes. They said that there was 1 black male, so there's definitely overlap. Since there's overlap, that means after we add up the individual probabilities of being a black kitten or a male kitten, we're going to have to subtract the probability of being both so that we don't double count it. So now probability of black or male, let's do these individually first. Probability of a black kitten. So they said here that we had 3 black females and 1 black male. That's a total of 4 black cats. And we need to find the overall number of possibilities as well. So we had a gray female, 3 gray males, plus the 4 black cats. That's a total of 8 kittens overall. And we said, again, we had 4 of them that were black. So now let's also find the probability that we have a male. They said that we had 3 gray males and 1 black male. So that's a total of 4 males out of 8 kittens total. So we're going to add 4 over 8 here. And now, since we've counted black kittens and male kittens, and some of them are both, we have to subtract the overlap. They said, and there's not a lot of overlap actually, we only have 1 black male kitten. So we're going to subtract that 1 out of the 8 kittens. And now putting all this together, 4 plus 4 is 8, minus 1 is 7. So that is a 7/8 chance of getting a kitten that is either black or male. On this problem, we have a basket containing 3 apples, 3 peaches, and 4 pears. You randomly pick a piece of fruit. We want the probability that it's an apple or a peach. So since we're dealing with an or, we have to worry about possible overlap between these groups. We don't want to double count anything. Can a fruit be an apple and a peach at the same time? And at least in this problem, the way it's written, it can't be. There might be some kind of weird genetically modified peach apple, whatever that would be called. You could probably buy it at Wegmans. But there's no overlap in this particular problem. So since these are disjoint, we can just find the individual probabilities and add them together. So probability of an apple or a peach. Let's deal with each one separately. For, let's see, overall, we have how many pieces of fruit? Because this is our denominator, our total possibilities. 3 plus 3 plus 4, that gives us 10 pieces of fruit. So that's always going to be our denominator when we're doing this. And now for the apples, we had 3 of those. So that's a 3 out of 10 chance that you get an apple. Or if we pick a peach, there's a 3 out of 10 chance of getting a peach as well. So adding those together, that's going to be 6 out of 10, which we can now reduce to 3/5. For this problem, we have a card being drawn from a standard deck, and we want the probability that the card is even or below 5. And just note that for this problem's purposes, an ace has a value of 1. Okay, so if we're dealing with an or, we have to ask, do these two groups have any overlap that we're going to need to worry about later on? Can a card be even and also be below 5? And yes, it can. 2 and 4 are both even and less than 5, so we're going to have some overlap here that we're going to have to subtract after we add the individual probabilities together for these two different groups. So now let's do that probability. What's our overall number of possibilities? Well, since this is a standard deck of cards, there's 52 cards overall that we have to choose from with each of these probabilities. Having said that, let's now deal with the probability of getting an even card. So remember that there's 4 of each number card in a deck of cards. We've got 4 aces, 4 twos, 4 threes, and so on and so forth. So even cards, we've got, let's see here, 2, 4, 6, 8, and 10. And then the face cards don't count. So that's 5 different types of cards that are even. And we said there's 4 of each of those, so that's a total of 20 cards, 5 for each suit that are even cards. And now we also have to talk about less than 5. Which cards are less than 5? Well, the ace, which counts as 1, and then 2, 3, and 4. Those are all less than 5. So that's 4 different sets of 4, because each suit has its own card that falls in those categories. 4 sets of 4 that are less than 5. So that's a plus 16 over 52 that we have to add in there. But now we have to worry about the overlap, because we've got cards that are even. This fraction gives us cards that are less than 5, but some cards fall into both categories, and we don't want to count them twice. So the cards that are both even and less than 5, that would be the 2 and the 4, and there's 4 of each of those, 4 for the different suits. So that's a total of 8 cards we have to subtract from that mess that we've acquired so far. So putting all this together then, 20 plus 16, that gives us 36. And now subtracting the overlap of 8, that's going to be 28 over 52. But wait, we can reduce this by 4s. So that's going to be 7 over 13 for the total probability. For this problem, we have a card drawn from a standard deck of cards. We want the probability that we get a 5 and a 6 with one draw of a card. So this is kind of a weird problem because they're asking for a card that meets both of these conditions at the same time. But now a card can't be a 5 and a 6 at the same time. It's either one of those or some totally different number. It can't be both. Since we can't have two mutually exclusive outcomes at the same time, this probability is just 0. It's like asking somebody to have their cake and eat it too. It's just not going to happen. For this problem, we have a card being drawn from a standard deck. We want the probability that it's a diamond or a spade. Since we're dealing with or, we're going to be adding probabilities together, but we have to ask, is there any overlap between these two groups that we'll have to subtract? Can a card be both a diamond and a spade? Well, it can't. These are different suits. Something's either a diamond or a spade or a heart or a club, but it can't be two of those suits at the same time. So because these are disjoint groups, we just add the possibilities together without having to subtract anything. All right, so probability now of either of these, the total possibilities, since we have a standard deck, is going to be 52. So that's our denominator. Probability of a diamond, there's 13 of each suit, including the diamonds. So that's 13 over 52. Probability of a spade by itself, that's also 13 over 52, and we're adding these probabilities together. So that's a total then of 26 over 52, which we can reduce to 1/2.